In this video, we're going to just be looking at some miscellaneous CLEP topics, kind of just like some loose ends that we didn't tie up throughout the course. And we're just going to start with, I think, oh yeah, function versus not a function. All right, so kind of the thing that you're going to be faced with is these questions, it's like, here's an equation, here's a graph, here's a table. That's one I've seen before. You know, which of these defines y as a function of x? That's one I know of. Okay, and so the graph is very easy. We know that, you know, if I just say function versus not a function, okay, a function, you know, it does its thing. It passes the vertical line test. But not a function is going to be something that, you know, maybe it like loops back on itself, right? When we go and we go to look, draw a vertical line through it, we hit it more than once. Okay, that's not a function. Okay, that's pretty easy. The table should also be pretty easy. Okay. Okay, if you see, you know, 2, 3, 4, and something like that, we're not seeing the same x mapped to multiple y's. That's going to be a function. What would happen that would cause this thing to not be a function is if we had, like, the same x going to different y's. Okay? You know, something like that. Okay? So basically the fact that I have 2 and 2 going to 2 different values, and that makes it not a function. Algebraically, what you're going to see is that if you have y equals, and then really any of the things that we're familiar with in this course, if you can write it as y equals, it's going to be a function. Okay? That's anything that was familiar, you know, some equation. Okay? What is not going to be a function is if you go to solve for y and you end up with a plus or minus. Okay? That is going to be what keeps you from having a function. You know, some function. Okay. So, for example, here's a couple. Usually they're going to write these equations implicitly, which means that x and y are just kind of like commingling on the same side of the equation. So you'd have to do a little bit of work to solve for y. Okay, I'll just tell you this first one is going to be a function. Okay, I'm going to add y to both sides, and I'll have absolute value of x equals y plus 21. If I wanted to solve for y by itself, I could say y equals the absolute value of x minus 21. I see no plus minus in there. I'm good to go. Okay, over here, the second one. I'm going to try to solve for y. I'm going to start by adding x to both sides. And then I'm going to solve for y by taking the square root of both sides. And when I take the square root of both sides, I need to remember the plus minus. And that's what's going to keep this thing from being a function. Okay, the intermediate value theorem is, in reality, a little more complicated than this. But what we're going to be always using it for in college algebra is that if you've got a function and it's continuous and it has a sign change, that sign change is evidence of a zero somewhere. Okay, so if you had, you know, some function that was given to you as a table of values, we could look at this table and say, okay, if f is a continuous function, you know, that's always going to be in the fine print. So, you know, maybe I'll just kind of write that. F is continuous. And we're looking and we're going to see, when does it change signs? It goes from 9 to 4, so it's still positive. Okay, it doesn't mean that there's not a zero between -4 and -2, because you don't know what's happening. It could go from 9 all the way down to -100 and then back up to 4. You don't know. But from 4 to 5, I'm seeing a sign change. Okay, then I'm seeing another one here. So it went from negative back to positive. Okay, and then another one when I went back to negative. Okay, so I've got 3 sign changes, which means that's evidence of at least 3 zeros. So it would be something like, you know, what's the minimum possible number of roots this thing could have? Well, 3, because I see 3 sign changes. Okay, So that means that f has at least 3 roots, or zeros, whatever you like to call them, on the interval, the x interval we're seeing, which is -4 up to 6. Okay. Since I know that -4 and 6 are not the zeros, I know that the roots have to come on the interior of that interval. All right, now we're just getting into the really random questions, and we're going to look at, which of the question in your notes packet is, which of the following will result in a perfect square for all integer values of x when added to 25x squared plus 4? So basically I said, what do you add to 25x squared plus 4 to always get a perfect square? Okay, well, if we're looking for something to be squared, and it's going to come back with, 25x squared plus 4, well, I know what I have to square to get 25x squared plus 4. I know that we're just kind of missing those outside and inside terms from FOIL. Okay, so you think, okay, 25x squared, that's the square of 5x. And 4 is the square of 2. So what I'm going to do is I'm going to actually FOIL this and see, what am I missing? I think that's the best way to approach this problem. So, and if you know how to complete the square from, some earlier algebra class, good for you. That's fine. You can do exactly that. Or you can do it this way and, see why it's true. Generally, when we show you how to complete the square, we show you why in general the first time, and then you just kind of remember what the trick is. Okay, so what I'm going to do is I'm going to actually FOIL this thing. 5x times 5x, sure enough, 25x squared. And the outside and the inside, 5x times 2 is 10x. And then 2 times 5x is another 10x. And then plus 4 on the outside. So see, I've got this 25x squared. I've got this 4. So I must just need to add these 20x's to get a perfect square. And sure enough, that's the answer choice A on your question. Pleasure. Okay, we would need to add 20x. And okay, so last unit we did some arithmetic sequences, but we didn't have any that were algebraic in nature. So when we looked at the arithmetic sequences, what we knew was that there was a common difference. So you got from one to the next by adding something, or maybe subtracting it. And it looks like the difference is I still have this x over 7 thing, and it looks like I'm subtracting 4. And then again, I'm subtracting 4. So that common difference is -4. And we had this formula that the nth term of an arithmetic sequence was equal to the first term plus the common difference times n minus 1. Okay, well, that common difference is equal to -4. And we know that the first term, this first term here, is x over 7 minus 21. So what I'm going to do is I'm going to say that the nth term equal to x over 7 minus 21 minus 4 times n minus 1. And then to get the 16th term, I'm just going to plug in n equals 16. And 16 minus 1 is 15. So I'm going to be subtracting 60 from -21. That'll be -81. Okay, which is one of your answer choices in there. Now, the last question I've got of this collection of miscellaneous problems that could potentially appear on some sort of standardized test is something from all the way back to the very first unit. And I think we did something like this then, but I don't know if we phrased it exactly this way. Okay, so we're saying if x equals -2 is the solution to this equation, what's the value of this other variable a? So what we're going to do is we're going to take -2, and we're going to plug it in wherever we see x. And then we'll just have it some equation in terms of a. It'll be easy to solve, and we'll just go from there. All right, so I'm going to take x to the third is -2 to the third, plus 4 times -2 squared, minus a times -2, plus 12 is equal to 0. This is negative 8 plus 4 times 4 is 16, plus 2a plus 12 equaling 0. And so I'm going to actually add the negative 8 to the 16. I'll have 8 plus 12 is 20. That's 2a plus 20 equals 0. And then from here, y'all know what to do with this. That's going to be negative 20, meaning a is negative 10. And I'm pretty sure that was answer choice C. And that's all I got for you on this video.